Okay, good morning. It's 9:20, so I will kick off. So this is rendering 3D worlds in C#, and I suppose this talk is a play in 4 acts. We're going to think a lot about the history of 3D graphics, and we're going to think about the history of games before we see some code. There's quite a lot to get through, so if you've got any questions, I'll grab them probably at the end or on Slack. Unless they're about maths, then I'll probably refer you to Wikipedia, I say, only half joking. Cool. So let me talk about me a little bit, obviously, all about me. I'm David, and I'm an independent software consultant based in London in the UK. I work for myself, mostly taking roles, mentoring developers, and doing strategic work for big UK .coms. I've done a variety of jobs with variably pretentious titles like Head of Engineering and Chief Technical Architect, Head Principal Engineer, which all sounds a lot fancier than it really is. I just love making things, and I love the people that make things, and I try and spend time helping them and doing cool stuff. So I've written a couple of kids' books about programming, websites, and games in JavaScript, available at all regional languages and all good bookstores, Get Coding 1 and 2, plug. But recently, just kind of to see if I could, I built a 3D renderer in raw C#. So why on earth? Why would you do that? So I know it's all a little bit pointless, really. But isn't that the fun of experimentation? There are lots of different answers to this question. But firstly, I really just wanted to see if I could do it. So often we're forced to live in this brutalistic corporate hellhole where the only things that have to exist for money, and those are the only things that ever get rendered into reality. So this is kind of the opposite of that. So 3D engines exist. If you want to build a game, you probably shouldn't do anything I'm going to do in this talk. It'd be a waste of time and effort. You should go and download Unity or Unreal Engine and make your awesome game. But if you want to do silly things to see what you're capable of, come with me on this journey. I'm not a graphics programmer, and I came to this topic pretty cold. Before we get going, I just want to caveat a few things about sequencing and history. So in a talk like this, we're going to be talking about technological advancement from a period where things were being invented and reinvented over and over again. I'm going to be talking about things in sequence here that appear to have come after other things, but in all practicality were probably being worked on simultaneously. That every single game I mention, there were doubtless other games that came before, or they were riffing on a similar theme, or they were influenced by peers in their local communities. So please do not feel slighted if I forget to mention your favorite game. I'm totally, absolutely sure it's awesome and important and legitimately amazing. Before we deep dive into 3D, it's important to understand what three-dimensional images, what 3D actually means. Your computer monitors are all two-dimensional. Even if you're using VR headsets, they're two-dimensional. They literally have two axes, an X and a Y axis. They render flat images. So when you try and draw by hand something that looks 3D on a 2D space, it often looks strange and wrong. The screenshot here from Rampage, an old game, is 2D. It's clearly trying to represent a 3D space, but no one would look at this and say, "Oh God, that's a really well rendered 3D image." It's not even pseudo 3D because there are only two planes, left to right and up and down in this image. It's not to scale. It's definitely not 3D. It's all really a matter of perspective. So making a two-dimensional image three-dimensional is not actually about the fidelity of the image, as some people mistakenly think. People think that it's all about quality, but actually it's about how an image captures perspective. And perspective is an art technique for creating the illusion of 3D on a 2D surface. So the correct use of perspective actually was one of the great inventions of 15th century art. It's often credited to Leon Battista Alberti in a book he wrote called, wonderfully titled, On Painting, which dates to 1435, the year 1435. Alberti outlined what is now known as linear perspective. And what linear perspective does is it plots a single horizon line with a vanishing point, and it positions elements along those lines heading towards the vanishing point to simulate depth. Linear perspective, though, is just one kind of projection. So that's the reason that both the picture at the top and the bottom there seem 3D. It's because they're capturing perspective. So what a projection is a graphical technique that maps three-dimensional points into two-dimensional space. It's an engineering and fine art discipline, actually, and can be learned. So this is not the same as being a great painter. It's a technical discipline. It's a mathematical exercise. And projections come in many, many forms, all defined by where the camera is supposed to be. I use the word camera loosely, where the viewer is supposed to be, and where the focal points are placed in the image. Accurate perspective projections are what makes something look three-dimensional in a two-dimensional space, converting those three axes into two axes. So one-point perspective is the most common three-dimensional projection in games today. It's the first-person shooter perspective with a single camera from the focal point of a main character. Over time, though, games have used other perspectives for various reasons. Early games often favored orthographic perspectives, the isometric rendering of 3D into 2D. We'd still, I suppose, consider these games 2D games, but they were technically representing three-dimensional space. They were technically 3D games, but it's not what people really mean when they say true 3D. Isometric perspective is really, really useful in games, especially in older games, because all the objects inside the 3D space remain the same size wherever they occur. And in early games, scaling things in size was computationally really expensive. So being able to design a single art asset that you could move around the pseudo 3D space without scaling, without changing, without swapping it out for another asset, because there was no storage space, was really important. It's worth remembering that when we talk about 3D today, what we're really referring to is polygonal 3D. And actually, gaming has this rich history of pre-polygonal 3D graphics that are worth considering, along with the journey we took towards high-performance polygonal 3D. So this is a screenshot from the very recent Unreal Engine 5 demo. It's due out in 2021 sometime. And you really have to marvel at the absolute beauty and sheer weight of research and technical excellence behind this screenshot. There are literally billions of polygons in this image. Millions of polygons on each rock, each decorated with 4K scanned textures mapped onto those objects. There's global illumination, modeled rays of light that bounce off surfaces. We've got depth of field effects, particle effects, material simulations, most of which are implemented in pixel shaders that run on specialist CPU cores called GPUs that are optimized for crunching maths. Modern 3D is the accumulation of 3 decades of work in polygonal 3D rendering. The fact that we can make images with this degree of fidelity is actually mind-blowing. It's amazing. I saw a joke floating around the internet, which is something like, "Oh, Epic Games are building Unreal Engine 5 to shame web devs who struggle to make websites run at 30 frames a second." And there's, I suppose, a little bit of truth in that. But really, to appreciate modern 3D, it's important to grasp the road that we traveled to the destination. I want us to appreciate some of the things that you might not think were really 3D, but secretly kind of really were on the way. So on the left we have Tempest, and on the right we have Maze War. So long before general purpose 3D, way back in the 1970s, we had what appeared to be 3D graphics in vector-based games. And I want this to really challenge our idea of what being 3D really means. So obviously Tempest isn't 3D, that's a 2D game. But if we look at the screenshot of Maze War, this is technically the first three-dimensional first-person shooter. It was written in 1973, running on a PDS-1 computer in this screenshot. And it was made up of what appears to be empty, hollow polygons. But it was actually something very, very different. So these polygons didn't really exist in the game code. They were the result of line drawing operations on vector monitors. And vector monitors are super interesting because they're not like the displays we use today. A vector monitor is not divided into pixels like a modern display. Instead it has more in common with the displays on an oscilloscope. It technically has infinite resolution. So this was a trend that continued into the early 80s, in fact. And at the top here we have a relatively well-known Star Wars game from I think 1983, and Battlezone underneath. So the surface of a vector display screen is a single layer of phosphor. It emits light wherever the electron gun hits it. This meant that if programmers were creative enough, they could manually, in their code, instruct the display to draw whatever shapes they wanted, just as if they were drawing lines on paper. Games like Tempest, Asteroid, and the early Star Wars arcade game here, and games consoles like the Vectrex, managed to look way ahead of their time. In some respects, they were a natural evolution from the very first video game, which was called Tennis for Two, which was actually played on an oscilloscope, and it was, I suppose, a proto-Pong game. The Vectrex itself actually was a fascinating console. It was born of a Smith Engineering employee working out a way to clear their stocks of surplus CRT vector-based displays. They found a bunch of 1-inch high displays that were originally manufactured for medical use. There was only actually one single run of the consoles because then they ran out of cheap screens, which as a result makes them relatively expensive collector's items today. But they did things like pen digitization, actually really ahead of their time, very cool. During the 70s and early 80s, there was actually this broad shift towards raster graphics displays. And you may have heard the terms vector graphics and raster graphics, but let's unpack what that really means. So compared to a vector display where you could draw anything anywhere, raster displays use bitmapped graphics. What that means is that the display is divided into pixels, usually directly mapped to an area of memory. So rather than the effective infinite resolution of a vector display, raster displays operate at set resolutions. You've all used them. You're literally using them right now. They're the screens you know and love. Raster displays provided a level of hardware abstraction over the low-level drawing of vector displays. Vector displays had to be redrawn repeatedly to keep the image on the screen, where raster was predictable, with fixed refresh rates and easier to standardize over. So raster displays were common, going all the way back to Pong in 1972 in games used a raster display, for instance. And over time, the use of vector displays became less and less common, with the arcade industry using raster displays by the 80s almost exclusively. There were obviously notable exceptions, like the Star Wars game on the previous slide. But the games of the 80s that featured 3D often used artistic technique to simulate 3D, which was really just a raster graphics approach to the earlier line drawing 3D vector graphics games. Just this time in higher fidelity with richer colors, because vector displays could only support up to 3 colors with special films. Occasionally, like in the case of Atari's iRobot in the top left here, no relation to the film or the book. Specialized hardware was actually built into the arcade cabinets to support drawing polygons quickly. This arcade machine had a custom 3D coprocessor, which you could really think of as the progenitor of the 3D accelerator market. So pictured here, we have iRobot, we have Falcon, and we have LucasArts' Rescue on Fractalis in the bottom left, which was seen as the first game to ever legitimately scare people when you encountered aliens and didn't know if they were friendly or not. We then entered this era of Sega's Superscaler series of arcade boards. So these arcade boards powered games like Space Harrier, Afterburner. Sega had become adept at sprite-based pixel art in their prior arcade games, and they'd started on this journey towards texture-mapped 3D by implementing hardware sprite scaling to provide perspective. So this kind of fast sprite scaling was far beyond the capabilities of home consoles in the mid-80s. They introduced what they called the Superscaler arcade graphics technology with Hang-On in 1985. The guy that designed these boards, Yu Suzuki, very, very famous Sega designer, is quoted as saying that the Superscaler games were designed as 3D games and then simulated using sprite scaling to produce the look of texture map 3D. And as a result, they looked way more impressive than early polygonal 3D graphics. Sega were great at art. In fact, Superscaler technology was astonishingly similar to the very, very hyped Mode 7 graphics mode on the Super Nintendo. So Mode 7 included hardware support to scale and rotate the background layer only of sprites on a scanline by scanline basis. So if you ever played on the SNES, you'll recognize this as the way that the race course effect, if you look at the screenshots, ignore Star Fox, that was something different. But F-Zero, Pilot Wings, and Mario Kart, the thing they all have in common is the background is a single skewed 2D sprite that rotates around a fixed point. It's the foundation of their graphics engines. And they use hardware sprite scaling in tons of games. It looked really cool at the time. So the funny thing is, Sega was so good at scaling and rotating sprites that it actually formed the foundation of their Sega Saturn console they released in 1994. It was actually very similar to the final Superscaler arcade boards in hardware design. So Digital Foundry, the YouTube channel, did an excellent retro game retrospective on the game Tomb Raider, where they used an emulator to unskew the Saturn's quad-based rendering engine, which actually favored over polygons. So as you can see in the top screenshot here, what that really meant is 3D games on the Sega Saturn were actually 2D square sprites skewed and mapped over the polygons to generate textures around the game world. Ironically, this gave the Saturn its reputation for being hard to program and probably contributed to its defeat at the hand of the Sony PlayStation, which made a large bet on true polygonal 3D. I find this screenshot amazing. And then we hit the early 90s. And in the early 90s, there was this slow and lumbering lurch into true polygonal 3D. And they were really, really rough, honestly. Like, all the way until the mid-90s, early 3D was exceptionally low poly, meaning that the 3D models that the hardware at the time could cope with were low in complexity. The engines were slow, and the art style possible with the really crude forms of 3D rendering at the time was really, really rough. Like, this stuff has not aged well at all. In fact, given the relative quality of true 3D in the early 90s, you can perhaps understand what Sega was thinking when they were designing the Saturn. They were kind of unwilling to dispose of 2 decades worth of 2D experience so quickly, especially when their pseudo 3D was kind of plenty fast and looked nice. That said, Sega themselves took their first stab at true 3D with Virtua Racing, and this was in the August of 1992, which was initially a proof of concept for exercising a new 3D graphics platform that they called the Model 1. The late 80s had seen a few polygonal titles from Atari and Namco, but none with the poly count and performance of Sega's Model 1 board. They followed up Virtua Racing with Virtua Fighter, which went on to become another huge hit and ubiquitous in arcades everywhere. So, while there were plenty of games reaching for real 3D at the time, it was probably the mixture of Mario 64 in September of '96, Tomb Raider in October of '96, and Quake in June of 1996 that really solidified what polygonal 3D games could actually be. Sega Saturn had shipped with home ports of Virtua Racing and Virtua Fighting very late in '94, but it wasn't until the release of the PlayStation and the N64 that the scene was really set for the mid to late '90s 3D game explosion. With those first games that felt like they really made complex 3D games mainstream. There were plenty of other games doing 3D between 1994 and 1996, but it's easy to remember just how ropey some of the game design and conventions were, because this was entirely new territory for game designers. So these 3D games really, these three games even, really locked down some of the conventions of gaming that stick around today. So we're talking about 3D camera control, first-person perspectives, and interactivity. Of these three, Tomb Raider has probably aged the worst, and this is due to some unfortunate control scheme choices made at a time when there were literally no default control schemes for 3D games. Mario 64 is still as playable today as ever, and Quake holds up entirely as the first real 3D networked multiplayer game that worked. So a bit of a quick recap before we go on. We've talked about three ways of simulating 3D through early video game arcade industry titles. There was vector line drawing that projected 3D. There was early orthographic projections to render isometric viewpoints. And there was sprite scaling to simulate 3D models. And then finally, true 3D polygons. But what I've not spoken about much is speed. And we've not even touched on the home computer market at the time. So there's kind of a parallel thread here, and that's 1990s PC gaming. The personal computer existed in an alternate universe from games development for consoles and arcades at the time. The IBM PC standardized in the early 80s, but wasn't really seen as a thing for play. It was targeted towards business users. We're still at the end of the 1980s microcomputer trend here, especially in the UK. So we have systems like the Atari ST and the Commodore Amiga being much more common in the home at the time. So that's not to say that there weren't games on the PC in the 1980s, but the kind of games you saw were often slow, occasionally text-based, and not very similar to the games popular on consoles at the time. You'd expect to see adventure games like the King's Quest series, Elite, Lode Runner, the Zork trilogy, text-based games. That's what people thought about when they thought of PC games. Slow, laborious, point-and-click adventures and simulations. Not graphically rich, fast-paced games like Mario or Sonic. It was kind of conventional wisdom that PCs literally were not capable of the kind of performance that more specialized gaming systems were. But I want to tell you about a game that's secretly really, really important. So, in 1991, a company called Softdisk put out the game Hover Tank 3D as part of their Gamer's Edge series of monthly discs. So this is a series curated by a man called John Romero. Softdisk have made a name for themselves as part of the burgeoning shareware scene, and this was one of just the many games they put out. They described it like this. Hover Tank 3D is set during a nuclear war. The player controls Brick Sledge, a mercenary hired by an unknown organization to rescue people from cities under the threat of nuclear attack, largely by political activists or scientists. Oh, how relevant. Both by the government and by large corporations. However, the cities are also full of mutated humans, strange creatures, armed guards, and enemy hover tanks, of course. Okay, so this sounds like it could literally be any other game of the era, right? But Hover Tank 3D was a little bit more important than that. Surprise, it's John Carmack. So the four people that were working on Gamer's Edge at the time were John Carmack, John Romero, Adrian Carmack, no relation, and Tom Hall. These people would go on to be the four founders of the prolific game studio id Software. And all these are wonderful 90s photos. I especially like the really the romance novel vibe in the photo of the right. That's totally my jam. In their evenings while working at Softdisk, these gorgeous, beautiful men were taking their work computers home with them and working on what would later become the id Software games. So the team had just cloned Super Mario Bros. 3 for the PC. So this was something at the time that was deemed completely impossible. Nobody thought smooth scrolling could reach the performance of the NES original on PC hardware in the mid-90s. In mid-1990. This slide is actually a screenshot from that specific PC port that John Romero put online, I think, for the 25th or 30th anniversary. They had sat for a week tracing, literally with pen and paper, the original game on a CRT television and cloning its gameplay. So they sent it to Nintendo, who politely declined the port. And not only that, they told them they couldn't use it. So that led to them building and releasing a game called Commander Keen, a suspiciously 2D side-scrolling platformer where you jumped on enemies with smooth scrolling on the PC. Yeah, not suspicious at all. In another world, Super Mario Bros. 3 might have been released on the PC, and we may have never played any of the future id Software games. So Hovertank 3D was the game they built to follow Commander Keen, and it was their first 3D engine. It took 6 weeks to build, and compared to other pseudo 3D engines at the time, it was really, really fast. So the reason it's really important is it was the game engine that would go on to form the prototype of the Wolfenstein 3D game engine, which later would become the foundation of the tech behind the game Doom. It would go on to develop Quake, its sequels, Rage, a load more Doom games. Carmack eventually goes on to serve as the CTO of Oculus VR and does civilian rocket flight. These games were renowned for their speed. It's what made them playable and addictive, along with being able to pioneer online multiplayer, game modding, open sourcing games, all because of these engines. And part of the reason these games ran so well is because of how their graphics engines worked and how they worked around the hardware constraints at the time. So Doom uses a technique called BSP, binary space partitioning, for its rendering, and we're not going to deep dive into that here. What we're going to do is we're going to start with Wolfenstein 3D and take a look at how its 3D renderer works. If you're interested in more information on the history of id Software, there's a really great book about it by a guy called David Kushner called The Masters of Doom from 2003. It's on Kindle, Amazon, Barnes & Noble, all good bookstores. It's a really fun read, and it's an interesting story through the history of arcades and the early PC gaming scene. I would recommend it. It's fun. So there are only two things you really need to know about making things run fast in 3D. Render as little as possible and do maths really, really quickly. I half joke, but it's kind of as true in 2020 as it was in 1991. The games industry today is full of clever optimization techniques to work out how to render the absolute least things possible. And we're going to take a look at a technique called raycasting, which was the basis of both the Hovertank 3D and Wolfenstein 3D game engines. You know, you could tell it was new at the time because they stuck 3D in both of the game titles. It was an early approach that was used to make things run fast. So I will refer to Wikipedia. Raycasting is the use of ray surface intersection tests to solve a variety of problems in 3D computer graphics and computational geometry. The term was first used in computer graphics in 1982 in a paper by Scott Roth to describe a method for rendering constructive solid geometry models. I always wonder who writes those really, really faux sciencey descriptions on Wikipedia. Wolf 3D uses raycasting to convert a 2D level design, a flat maze, this is one of the maps in Wolfenstein, into a 3D projection. And we're going to dissect and clone this behavior in code. So how could we convert that map, this real Wolf 3D map, into a 3D world that we can run around? So I've drawn a really crude map on this slide. It's a big empty room with 2 blocks inside of it. Towards the bottom of the map, I've drawn a circle, which represents our camera, facing north. If we were to imagine that our camera was casting rays, literally drawing straight lines for every part of its field of view, it might look something like the lines drawn from our camera point. So the number of rays we're casting here isn't that important, but in a real-world example, it'd be related to the focal length of a camera. So the further a ray has to travel from its origin, the camera, before it makes contact with something, the further away that thing is. So we have 8 rays in our example here. Now, imagine that we record the distance that each of our rays travels and fill up some columns. The further a ray travels, the fewer pixels we fill up in our column. So our first ray was really close to this left-hand block that you can see in the top right there. So we fill up quite a lot of pixels. The second ray is clipping the side of our left-hand block. Again, we fill up quite a lot of pixels, a little bit less than the first ray. The third through the 6th rays are shooting way off into the distance before they make contact with a surface at the very back of the room. So we're filling up almost no pixels at all. And once we reach our 7th and 8th rays, we're connecting with the right-hand block again and filling up our columns. So represented like this doesn't look like much of anything. These are just crude hand drawings and they're not very accurate. It doesn't look like 3D. But allow me to perform a magic trick. If we take our column of pixels we filled in vertically and center them, making sure that there's the same amount of space equally divided above and below our pixels, hey, look, that looks like a 3D world. So it's got a wall in the far distance, there's some blocks on our left and right that are near to us, and this is fundamentally how ray casting works in practice. You shoot a number of rays, scanning from left to right, and you measure the distance they travel before they connect with a surface. If the surface is solid, the ray stops, and if the surface isn't, it can continue to travel and connect with other surfaces. So this approach is faster than other rendering techniques that order objects on their Z index, how far away from the camera something is, and then render them furthest away object first, which was one of the competing techniques at the time. This approach, while absolutely fine, it requires multiple passes over pixels to correctly construct the image. So you end up drawing again and again over the top of things. It's not very performance optimized. Whereas this just requires a single line of horizontal rays. It's quite fast. What we do is we set a max range on our camera. So our rays simply give up if they don't make contact with anything far off into the distance. So we can now express the number of pixels in any given column as a percentage of that total distance at the max range of our camera. We calculate the percentage of vertical pixels to fill up as the distance traveled divided by the camera range times 100. By doing this calculation and measuring the distance a ray travels, and by knowing the target height of our screen, we can easily calculate how many pixels to draw. So by doing this, we project our 2D plane into 3D space. We've looked at how we can use raycasting to determine the distance between an arbitrary camera and surfaces in a 2D space. But how do we really turn this into an image? So the simplest way possible is we cast a single ray for each and every horizontal pixel of our target output image. So in our worked example previously, we're only considering 8 rays that we cast. It's not computationally too expensive, though, to just cast more. So for a target resolution of 1024 by 768, we'd cast 1024 rays, 1 for each horizontal pixel. Similarly, for a resolution of 1920 by 1080, a full HD image, we cast 1,920 rays. So let's build our own 3D engine. Let's do the thing. We can do this. I suppose this is kind of a .NET conference, not a history of video games graphics session, so I should probably show you some code. What we're going to do is we're going to define our own map format. We're going to write the simplest raycaster I can fit into some slides, and we're going to do 1 or 2 bits of scary looking maths for someone like me. When I say someone like me, I mean someone that stopped studying maths at 16. And then finally, we're going to render our own 3D world. So when you consider this, our finest 3D game level, we're going to be astounded by our 2 cubes in a room. I can just feel the cover shooter gameplay brewing right now. I hear you yell. This is Gears of War 20. So this is a bog standard file, new project, default .NET Core 3.1 console application. I've added 2 static variables. Max camera range, which I've set to 50, and the world's most glorious string array called world. What we're going to do is we're going to put our level data into that string array using my innovative new data storage format. I've got a name for it. It's called Hashes for Walls, coming 2021 to take the gaming world by storm. For the sake of this example, any space, literally any space character, has a height of 0. And any hash has a height of 1. I know, innovative. We're also setting up a camera location as a location 2D type. So this is just a struct that contains 2 properties, X and Y. There is nothing else going on in there. The camera is going to be located 10 characters in and 7 rows down in our array, facing to the right by default, which I think puts it about here. So our array, what's an array? How do we express an array? Our array is just a list of sample points. A sample point has a location that it's sampling, here, along with storing the length of this part of the array, here, and the total distance traveled to get to this location, here. The idea is that as we write code to walk through our map, we're just going to append a new sample point to this list as we go on. The final sample point is always going to be the one that connects with a surface, so it will always be the last sample point in our array. You'll notice we have a property in the sample point called surface here. In our map, we only actually have 2 kinds of surfaces, a wall or nothing. And when we detect a surface later on, we're going to store a reference to the surface that we're detecting here. So there's a lot going on here, and I want to walk through it really slowly. We're going to create a new result, an array of sample points, exactly the width of our desired rendered image. Remember, each horizontal pixel needs a ray casting. We're then going to perform a for loop for each pixel in our target horizontal resolution and shoot a ray. We work out our X value, the angle of the ray that we want to cast, by taking our column number and dividing it by the render width and subtracting 0.5. So this works out exactly where we're pointing our ray on our plane. It effectively takes the desired camera angle, splits it into columns, and then positions the camera in the center of the column we've calculated the location of. We create our origin sample point at the location of our camera. And then we're going to work out which direction to cast our ray. Let's zoom down a bit. So this is one of those maths things that you weren't paying attention to in school. Don't worry, neither was I. I had to look this up at age 35. So a radian is a standard unit of angular measure. It describes how many degrees around a full circle that you are. Here, these radians. So the direction in degrees that we want to cast our ray to is pi divided by 180 times the direction in degrees of our camera. So that computes our radians. This actually should be called direction in radians, I think. And what we're doing is we're returning a cast direction object, which we create from this final output, which works out which way we're pointing on this circle. So a little bit more maths that you might have been sleeping through in high school. Our cast direction object contains the sine and the cosine of the direction we provided that we expressed in radians. Now, remember that radians are just a maths word for what direction on the circle are we pointing. So sine and cosine are two of the main functions used in trigonometry, and they calculate the ratio of sides of a right-angled triangle. In our case, they're going to help us work out how far to the left and how far to the right we're going to cast our rays from our starting point. Ooh, all the code. So this is the core of our ray casting algorithm. What we do is we loop forwards infinitely, walking one step following the shortest path the ray can take. Now you could express this with recursion, but a while true loop is easier to comprehend here. What we do is we use the sine and the cosine along with the current x and y value to calculate what the length of one step forward would be on both the x and the y axis. So we call this function twice, and if you notice carefully, we flip cos and sin here, and y and x and y. We compare the length of each step, and we choose the shortest path once we know which it is. Once we pick the shortest step, we call a function, or a method even, called inspect, telling it to either shift 1x or 1y. Inspect returns a sample point, which will keep a reference to any detected surface in. If the surface has no height, well, we continue, we loop onwards. If we're at our max camera depth, we return the ray path in its entirety. And if we reach something with height, amazing, woohoo, we found a surface. So we store our current sample point at the end of our list, and we return our complete traced path. So let's take a look into how we determine what the next step to take is, this next step on the line. So what this block of confusing looking code does is, given an angle in degrees and a pair of coordinates, it calculates the next step forward along our line. We call it with the sine and cosine values that we created that were held inside our cast direction object. And this feels really mathsy, and it was certainly an eyeful when I first tried working it out here. So what we're doing is, to calculate an x next step, we take our cosine value, which we call run, and if it's greater than 1, add 1. If it's less, we subtract 1. So we're kind of walking through a 2D array. This is inverted when we call the methods for our y step, with the sine value becoming the run and the y value having 1 added or subtracted from it. We record this change in length, and we generate a new location 2D coordinate. If the first value is x, we just return that location because it's not inverted. If we've called this function with our sine and cosine and x and y inverted, we just call this little flip xy extension method, which just literally makes x equal to y and y equal to x. There are likely prettier ways to express this concept. It's a bit of a mind bender, but it's what I have for the moment, so we're going to run with it. Our inspect method shifts either x or y by 1, depending on if x or y was the shortest path when it was called. So it calls the detect surface function, which converts our double down into an integer. So we've got a position here on our grid, and we want to convert it to literally x, y coordinates in our string array. And then we call our surface at function, which just checks by grabbing yx. It grabs a single character from our string array. And if it's a hash, it returns a surface with a height of 1. Otherwise, it returns nothing. So these values are then consumed by the loop back up in the ray function, which evaluate this response to work out whether the ray has collided with a surface or not. In a more comprehensive implementation of this, other characters could return surfaces of varying heights, and rays could continue onwards past things that were only partially obstructing the view, rather than in our implementation here where we just stop as soon as we reach a surface. Even in our cool map format of hashes for walls, different characters could be used to return different surfaces with different characteristics, which could correlate to different visual textures. So after casting our rays, we have a total distance value for each point on our horizontal axis. But we need to do a little bit more work to convert this to an image that might look like something. I've actually split these steps into two to make them a little bit more explicable, but you could merge both our cast rays function here that scans across and our render bitmap method if you really wanted to. The bitmap renderer is responsible for taking our array of completed rays and working out how many pixels to fill up in each of our vertical columns like we did by hand earlier. We're then going to write the bitmap to a memory stream and save it to disk so I can open it in an image editor. There's literally nothing interesting here at all. And we're gonna dive into our height calculations now. So this looks very scary at a glance, but it's not that bad. So firstly, our image width and image height, we're going to just use, say, 1024 by 768, in this case, a standard, if small, in 2020 resolution. So first, we're going to create a new image using the wonderful image sharp library, really great library. And we're going to set the desired width and height. So image sharp is an open source image manipulation library written in pure C#. It doesn't rely on any legacy interop. It's fully cross-platform, unlike many of the legacy image manipulation APIs we've had access to in .NET before. And we're going to loop around each sample point in our column. So the column integer here is also our x-coordinate in our output image. What we're going to do is we're going to work out the number of pixels we need to fill in. So the max possible height is the image height times the surface height, in our example either 0 or 1. And then we work out the height as a percentage of the distance traveled. I'm also here dividing distance traveled by 2.5. This just means that our walls can be a little bit taller in the output image. You don't need this here, it just felt better when I actually saw this with my eyes. And then we're calculating our vertical padding. So this is the space above and below the pixels in each column that don't contain our surface. We're taking our full image height, subtracting the height of our pixels, and dividing by 2. So now we get to loop over our y-axis, starting at the vertical padding number to skip the top portion of the image, and then we loop up to the image height minus our vertical padding to skip the bottom portion of our buffer. And we basically are just leaving the same amount of space at the top and bottom of the image by running this loop. And then we're just filling in our new image here, we're filling it in with a texture. So I'm kind of cheating here. So the texture is just the red, green, blue value 200, 200, 200, a kind of murky, white, horrible color, honestly. So it's very difficult to visualize what this is doing. So why don't I just show you? Like, how cool is that? Oh my God, like we have a ray traced image, sorry, ray cast, not ray traced image in our output directory. This is that code. It felt like a bit of a long journey, but we're actually still inside 200 lines of code in total here. And we've only done like 3 bits of maths, literally. You can see our walls projected towards our focal point in the distance, and we've got our 2 blocks. That's some AAA game design right there, 2 blocks standing there in white. Well, murky, off-white. So I don't like the fact that this just looks flat. I want to update our code to call a new select texture method. So we're going to do some really quick back of the envelope maths here and treat RGB 200, 200, 200, our off-white, as the maximum brightness that we can render. I'm basically inventing global illumination. And it's murky grey. The further away the wall is from the camera, the dimmer that we make the pixels. And what this does is it kind of simulates fading off into the distance. In a real game engine, we'd likely use this function to look up a texture and map pixels from a source texture on and project them onto the walls we're creating. But for now, flat colors are going to work for us. So this is relatively simplistic. We just work out a percentage of the total 200 and we set our RG and B values to it. That's all we're doing. So let's take a look. Look at that. I love it. It's a black and white image that represents our string array map rendered into 3D with our own raycaster. So we're doing a projection of a two-dimensional axis into three-dimensional space. That's pretty cool. I like it. I love it. So let's talk about floors and ceilings. So it's probably quite apparent that if I only have a 2D array, I don't really have any textures for the floor or the ceiling. There's no notion of height, which actually there was no height in Wolfenstein. There was no height in Doom. It was all simulated. So see this gradient. I like this gradient very much. Thank you, thank you. I made it in a minute or two in paint.net. My finest gradient work. It might not seem like much, but it's mine. So the reason I love this gradient is I can use it to cheat and provide additional texturing to the floor and ceiling of my raycaster, while literally writing one line of code. Well, two, I suppose. Instead of creating our world from a blank image and then filling in the pixels over the top of it, all I'm going to do is just load this gradient into my bitmap before we render the world, and I'm going to resize it to the resolution of our target image. And it'll come out looking like we had a floor and ceiling all along. I mean, I could possibly put carpet down and a blue sky. So it's especially sneaky because our world is still technically a 2D plane projected into 3D. But it's exactly how all the games worked. They cheated. Always cheat. See? Doesn't that just feel a little bit more real? This is a screenshot of obviously a slightly higher resolution render. What I did is I crammed the renderer into a WinForms UI, WinForms represent, so I could hook up keyboard controls. Like, you'll probably laugh, but it's just a picture box control, and all I'm doing is taking the byte array of the bitmap and setting the bitmap in the picture box 60 times a second in there. But you know what? Like, I've got 60 frames a second, playable, big room with 2 blocks. Good enough to play with, you know? Wiring up controls in WinForms is a simple task. I'm just subscribing to the onKeyDown event that comes built into WinForms and adjusting the location 2D property and my camera to add first-person style WASD controls. I think I literally spent 15 minutes in total hooking these bits up into WinForms just so I could have fun swinging my camera around in real time. A switch statement that updates a property is all it took. I was kind of almost alarmed at how simple it was. There is a sneaky little bit of maths hiding at the top there, though, which calculates the movement delta for each key press or mouse movement. It relies on using the same sine and cosine operations to work out which way we should swing the camera based on the left and right and up and down offsets of the pixels or keys. And there's a magic number of 0.35 which felt right, which I suppose technically is a mouse sensitivity option. I also crammed it into a Razor Pages file. I literally pasted all the code into the code behind and stuck a web form in front of it. And the really fun thing about this demo is that it lets you edit the map in the text box and then just put a number in for the camera angle and click submit, and it will render a new world in your web browser. I mean, honestly, I just did it to see if I could, to see if it would work. So there are plenty more places that we can take this prototype. It's missing texture mapping on the walls, but we have a place for it in our code. We could implement surfaces that don't occupy 100% of the height of the space that they're encountering. So we could put half-height walls in and really build Gears of War. We could implement different surfaces like glass materials that the rays continue traveling through, and then you combine the colors of the pixels that the ray encounters as it passes through them. Obviously, this code really isn't performance optimized, and realistically, it's not the kind of code you write if you were building a 3D game today. But to me, it's an interesting curiosity. It's a technique from a more resource-constrained time. The languages we have today are certainly capable of doing what was significantly harder then, in a lot less code. If you want to build games today in C#, use Unity, use Unreal Engine with C# bindings, use Monogame. But I hope you've enjoyed coming on this journey with me, just how old games hung together. You can get the code. So the code for this is available in a gist here. Paste it, play with it, have fun, quick, screenshot it, because there's some more slides. I'm going to conspicuously wait for like a minute so anyone can write that down if they need to. I will paste it in the Slack afterwards, don't worry. So the most obvious question when we're talking about ray casting is, hey, is this the same as ray tracing on my GPU? Well, sort of. This is an incredibly scaled back example of casting rays, the modern version of which is more often called ray tracing. And the terms were used interchangeably at one point in history, but they definitely mean different things now that certainly NVIDIA has co-opted the term. So when you hear ray tracing or RTX cards today, they're applying the same core concept, shooting rays of light through a 3D space. But what they're doing that's different is instead of using the rays to produce a 3D projection, they're normally using the rays to add lighting to already rendered 3D polygonal meshes. They use rays that bounce from one surface to the next, changing the way light and color is output in the resultant image. It's really, really clever. It's really resource hungry. And instead of just scanning left to right, they literally cast rays for every pixel. Actually, the way that they optimize for performance in modern times is they subsample an image. So they take a lower resolution render. They then cast the rays across every single pixel of that lower resolution render, not just for each horizontal column. And then they upscale the result that's ray traced over the subsampled image to enhance the render quality of a larger or higher res scene. So it's really cool. They basically use the same kind of AI upscaling you see when people take old movies and upscale them to 8K. If you're interested in this, I'd really recommend watching the Digital Foundry teardowns of Quake 2 RTX. So it's a port that NVIDIA produced to demo their RTX cards where they made a real-time ray-traced version of Quake. And you can see the digital noise floating around. It's really excellent. So I want to leave you with a small anecdote about a question I had when I was 10. I remember trying to play Doom on an underpowered 486 and struggling with performance. One of the options was to reduce the size of the window that was built into the game. You could shrink literally the rendering window and it would go faster. Similarly, I also played a lot of Doom on the 32X as one of the several owners of that short-lived Mega Drive add-on in the UK. It too rendered in a smaller window, and I remember wondering to myself, why is it faster to run Doom when you reduce the viewable game size? And in writing this talk, I realized that of course it's because there are less pixels to render. So Doom's BSP engine wasn't a raycaster, but it had similar performance constraints. And by simply reducing the screen real estate, the rendering sped up. So I hope this talk has inspired you to try and work on something you didn't think you could do. I approached this topic with the trepidation of someone that hadn't studied maths in half my life to any particular high level. And I had a load of fun working out all the details on the way. I'd never written a 3D render of any kind before. I'm not a graphics programmer, but I want to remind everyone that programming for fun and not just for your job is totally okay. Like, do fun things. You're going to love it. I'm available on all of the internet. Tweet at me, tell me I know nothing, tell me I forgot your favorite game, tell me you love me, ask for the code. I'd love to hear from you. And I really want you to all enjoy the rest of the conference. Thank you very much.